Okay, 5.5, counting techniques. Counting plays a major role in many diverse areas, including probability. So in this section, we're going to look at special types of counting problems and develop general techniques for solving them. Okay, so first of all, we've got the multiplication rule of counting. If a task consists of a sequence of choices in which there are P selections for the first choice, some number Q selections for the second choice, R for the third choice, and so on, then the task of making these selections can be done in this many different ways. You just multiply. A good way to see why that is to make a tree diagram to start with. So let's say you have 2 pair of pants, jeans and khakis, and 3 shirts, red, yellow, blue, and you want to know how many different outfits you can make. Well, with something called a tree diagram, we can say, if we have a pen, we can say, oh, there's 2 options for my pants, khakis and jeans. And then for every one of these, if I'm wearing khakis, I can wear a red shirt or a blue shirt or a yellow shirt. If I'm wearing jeans, I can wear a red shirt, a blue shirt, or a yellow shirt. And if I follow each path, I can see that, hey, khakis with my red shirt, khakis with my blue shirt, khakis with my yellow shirt, jeans with my red shirt, jeans with my blue shirt, jeans with my yellow shirt gives me 1, 2, 3, 4, 5, 6 different outfits. Notice that's the same as 2 times 3. 2 options for the first choice times 3. So this is actually our fundamental counting principle. Whenever you're counting something up, you multiply. Remember before when we talked about how many options are when you roll 2 dice, right? A pair of dice. And we said there's not 12 options. There's 36 options because there's 6 on each die. Okay, so that's going to be important. This tree diagram is really useful if you need to know exactly what all your options are. You can get a list of them. But notice it becomes unwieldy after, what if I wanted to add in shoes and I had 3 different pair of shoes, right? And that would considerably lengthen my tree diagram, but all it would do over here is say, oh, now I have 18 outfits that's possible. Fundamental counting principle. Okay, for example, the fixed price dinner at this restaurant provides the following choices. Appetizer, you can get soup or salad, right? 2 choices for appetizer. Entree, you can get baked chicken, broiled beef patty, baby beef liver, or roast beef au jus. So 4 choices for your entree. Dessert, you can get ice cream or cheesecake. How many different meals can you order? All I got to do is multiply them together. 16 different meal combinations. Okay. The International Air Transport Association assigns 3-letter codes to represent airport locations. For example, the code for Fort Lauderdale International Airport is FLL. And we know that the code for Dallas-Fort Worth is DFW. So how many different airport codes are possible? Okay, well, if it's 3 different letters, the first letter, we have 26 choices, right? A through Z, there's 26 of them. And notice they can repeat, so just because I used a F here doesn't mean I can't use it again, so I still have 26 choices. And then for the third letter, I have 26 choices. So let's see what that is. 26 to the 3rd power, 17,576. different airport codes available if they're 3 letters long. Okay, notice this one says without repetition. 3 members from a 14-member committee are to be randomly selected to serve as chair, vice chair, and secretary. How many different committee structures are possible? Well, if there's 14-member committee, then there are 14 ways that I could choose my chairman. Now, what's different about this one is that once we've elected Joe for chairman, right, then he can't also be vice chair. So there's only 13 people left that could be vice chair. And so once Fred is vice chair, Joe and Fred are not available to be secretary. So that leaves only 12 people that you can choose. So that would be 14 times 13 times 12, or 2,184. So when we're using this fundamental counting principle, be sure and consider whether repetition is allowed or not. Okay, if n is greater than or equal to 0, then the factorial symbol, which is an exclamation mark, so we'd say n factorial, is defined as follows. And this is n times n minus 1, dot, dot, dot. So in other words, if n is 10, this would be 10 times 9 times 8 times 7 times 6 times 5, blah, 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 all the way to 1. Okay, 0 factorial is just understood to be 1. Okay, how many ways can you get $0? 1, you don't get anything, right? And 1 factorial, of course, is 1 because we're already down at 1. Okay, so you've been hired as a book representative for Pearson. On your first day, you must travel to 7 schools to introduce yourself. How many different routes are possible? Well, if you got to go to 7 schools, then you can go to any one of those 7 first. And then once you're at that school, there's only 6 left for you to go to. And then there's 5 left for you to go to. And then there's 4 left. And then 3. And then 2. Until finally there's only 1 left. Right? So you could put that in your calculator. And this one might not be too bad. But what if there were 25 schools? Imagine this would be 25 times 24 times 23, dot, 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 times 3 times 2 times 1. What are the odds that you're not going to make a mistake punching that in your calculator? So if we are multiplying numbers that decrease by 1 and go all the way down to 1, we have this special notation, 7 factorial, and this operation is on our calculator. Okay, so if you go into math and back over to probability, then you'll see that exclamation symbol in there. So you hit the number first, so I'm going to hit 7, then math, then over to probability, and go down to the exclamation point, and this will be entered on your calculator, and you hit enter, and you get 5,040. Okay. Now notice factorial is only used when you go all the way to 1, so I could not have used it on those 2 previous examples, right? And I couldn't have used it on that first example or second, because this is where you have to go down by 1, so repetition's not allowed. Yeah, and the first one where we just had menu items, you know, there's no ordering of that. Okay, excuse me. A permutation is an ordered arrangement. This right here, underline that, ordered arrangement in which R objects, some number of objects, are chosen from some number of different objects, okay? And R, of course, has to be less than N. If you only have 2 apples, you can't choose 5, right? You only have 2 to choose from. And repetition is not allowed, okay? The symbol, this, represents the number of permutations of R objects selected from N objects. Okay, so this would be, let's say this is 5 and 2. Okay, this is 5 permutations taken 2 at a time. Okay, so the N objects have to be distinct, different. Repetition's not allowed, and order is important. Then we have this formula. Notice we use that factorial. But also, you might have noticed when you went into that math probability, you should have also seen this symbol right here, right? NPR. So my calculator will do this without using the, the factorial. Let's look at that. Okay, betting on the trifecta. Okay, and how many ways can horses in a 10-horse race finish first, second, and third? Okay, so from what we said before, one thing I can do is just say, oh, well, there's 10 horses that could come in first, and then there's 9 horses. After that first one crosses the finish line, then there's 9 choices left, and after the second one crosses, there's 8. So 72 times 10, 720. So that's one thing we could still do. Okay, but we could also say, oh, this is because there's 10 horses, and it's a permutation because the order matters, right? We're ranking them first, second, third. The order matters. That's the most key thing. The order matters. Okay, and we're talking about 3 positions. So on your calculator, enter 10, go into your probability, and choose that NPR, and then 3. Okay, and notice you should have gotten 720. So on this one, it's probably easier to just do this. But what if there were 100 horses and you wanted to know about the first 10 places? Right? Then this gets a little unwieldy. This is the same length. It would be 100 permutations taken 10 at a time. All right. Okay. Now, a combination is a collection without regard to order. That's the important part. In which R objects are chosen from N distinct objects, again, without repetition. And here's the symbol. Instead of a P, it's a C for combination. Okay, an easy way to read this also, combinations, a kind of a keyword for a keyword is not always in there, but a keyword for permutations is the word arrangement, arranging. A keyword for combinations is choose. You're just choosing and the order doesn't matter. So you can read this, N choose R. Right? You've got N and you're going to choose R of them. Okay, so here's the exact same idea. There's got to be N different objects. Repetition's not allowed. Order is not important this time. Notice the formulas are similar, but not exact. But what we're interested in is I have that on my calculator. Okay, so remember, in a permutation, order is important. In a combination, order is not important. Because the first thing we've got to do now, when we're trying to count things up, is ask ourselves, permutation or combination? Well, does the order matter or does the order not matter? Okay. Let's see, how many different simple random samples of size 4 can be obtained from a population whose size is 20? Okay, so I just want to take a random sample. Does the order I take them in matter? No, I'm just getting a sample. Okay, if I choose Joe, Fred, Bill, and Jill in that order, even if I choose Jill, Bill, then Fred, Joe, That's still the same sample of 4. The order I choose them in doesn't matter. I'm just choosing 4 people randomly. Okay, so the 20 individuals in the population are distinct. Okay, 20 different people. In addition, the order they're selected is unimportant. So the number of simple random samples of size 4 is a combination of 20, choose 4. And we can put that on our calculator. Let's see, 20, go into the probability and choose the combination one this time, and we get 4,845 different samples of 4 individuals. Okay, sometimes we want to arrange objects in order, but some of the objects are indistinguishable, right? In other words, not different, okay? Non-distinct. A lot of times books will call this permutations with like items. That might be easier to remember. Some of them are alike. Okay, and then we get this formula. Okay, so it's n factorial. It, again, n is how many total objects you have. And then down here is how many of them are alike, how many more are alike, how many more are alike. So once again, the easiest way to understand this formula is just to use it. So how many different vertical arrangements are there of 10 flags if 5 are white, 3 are blue, and 2 are red? All right, so 10 flags. Let's just look at what that means to start with. 10 flags. Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Never claimed to be an artist. Okay, and I'm going to make this real easy. 2 are red. Okay, 3 are blue. And 5 are white. So there's one arrangement, right? There is one arrangement. Now, if these were all different colors, if there was 10 different colors, and I changed the order of these 2 flags, I'd have a different signal, right? But since they're both red, if I just flip those 2 flags, it does not give me a different signal than that. So that's what it means, right? Okay. Okay, so our formula is, okay, we seek the number of permutations of 10 objects. Okay, 5 are white, 5 are the same. 3 are blue, 3 are the same. And 2 are red. Now, one way to double check this formula is if I add these numbers down here, they better add up to this number on top. Don't forget when I enter that in my calculator, I need parentheses around it, right? Okay, so let's do it. 10, go into your math, factorial, divided by, don't forget your parentheses, 5 factorial times 3 factorial times 2 factorial. And we get 2,520 different signals. Okay? Does that make sense? All right, so then let's just look at some examples. In how many ways can 15 students be lined up? My first question is, does the order matter or not? Okay, well, let's see. If I'm at the head of the line, does that make a difference to me if I'm at the back of the line? You bet, buddy. You bet. Order matters in that line. Me at the head of the line, and then Joe, and then Fred is different than Fred first, and then me, and then Joe. Right? That's two different lines. Okay, so technically it's 15 because any one of us could be the head of the line. And then once one of them is there, it's 14. And then there's 13, dot, 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 all the way until there's only one person left to get in the line. So this is 15 factorial. Okay, and notice that my calculator gave me an answer that looks like this. 1.307 674368 674368 E12. So I have to be able to read my calculator. This is a giant number, right? 15 times 14 times 13, on and on and on. So what this is giving me is it's giving me my answer in scientific notation where 12 is the exponent. Okay, so that means I've got to move this decimal over 12 times. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I've got to add 3 zeros to this number. Okay, so that's how many different lines. What do we have here, man? 1,307,000,000,000, blah, 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 lines with 15 people lining up. Different possible lines, right? Okay. A Social Security number is used to identify each resident of the United States uniquely. The number has 8 digits from 0 to 9. How many Social Security numbers can be formed? Okay, so does the order matter? Yes, it does, because just rearranging those numbers makes a different identifier, right? Okay, but I can't use my factorial because it's not, the numbers aren't, it's 8 digits, it's not 8 times 9. It means, oh, I can use any number from 0 to 9, so that's 10 options on the first number. And then on the second one, because someone's social security number can be 555 734 2218, right? 2215. I could use them multiple times. So this is 10 multiplied by itself 8 times, or easily as 10 to the 8th. So that would be a 1 with 8 zeros. Oh, only had 6 zeros on it, sorry. Oops, I had 7 zeros, sorry. Okay, so now notice, oops, all of a sudden it converted to probability. Okay, so we can use these counting techniques along with how we calculate probabilities, right? To now answer a lot more probability questions, because remember what it means to be probability is just you count the number of ways your particular event can happen, and that's what goes in the numerator. And in the denominator, you count the total possible ways that that event can happen. Okay, so I've got to be able to count for the numerator and the denominator. So the probability of correctly guessing the Social Security number of the President of the United States, well, that would be one Social Security number you're guessing. That's your event. Out of how many possible number combinations are there? 100 million, right? Okay, and actually 3, 4, 5, there's not, I don't know where this question, I don't know if that's a typo or not, but there's 9 digits in a Social Security number. Okay, so really, if this was an accurate problem, we'd have an extra 0 on that. Okay. All right. 4 members of a 50-person committee are to be selected randomly to serve as chairperson, vice chairperson, secretary, and treasurer. How many different leadership structures are possible? Okay, so it's asked me to count this thing up again. So my first question is it a permutation or a combination? Does the order matter? Once we've selected a chairperson, can that person also be the vice chairperson? No, right? So the order matters. It's a permutation. Okay, we got 50 people that we're choosing from. We've already said it's a permutation, and how many are we going to line up? 1, 2, 3, 4. And right there it says 4. Okay, so we can do that on our calculator. 50. Go into your probability. Choose the permutation option. And then 4. So 5,527,200. Okay, let's look at this one. In the U.S. Senate, there are 21 members on the Committee of Banking, Housing, and Urban Affairs. 9 of these 21 members are selected to be on the Subcommittee on Economic Policy. So how many different committee structures are possible for this subcommittee? First question, is it a permutation or combination? Does the order matter? No. Notice the difference between these two questions. These people are just going to be selected to be on a committee, right? There's no ranking. There's no chairperson, vice chairperson, secretary. There's no ranking. If I choose, Joe, Fred, and Bill, it doesn't matter if I chose Bill, Fred, and Joe. They're still going to be on the same committee, or Fred, Joe, and Bill, right? Same committee. Order doesn't matter. It's a combination. So there's 21, and we're going to choose 9 of them. So on our calculator again, it'll do those calculations for us. 21, just make sure you choose the combination option. 21, choose 9. So 293,930. Different subcommittees that could be formed. Okay, in the Illinois lottery, an urn contains balls numbered 1 to 52. From this urn, 6 balls are randomly chosen without replacement for a $1 bet. A player chooses 2 sets of 6 numbers. To win, all 6 numbers must match those chosen from the urn. The order in which the balls are selected does not matter. What's the probability of winning the lottery? Okay, so first of all, let's just see. Let me read this again, because why does it say 6 balls are randomly chosen? A player chooses 2 sets of 6 numbers. All right, so to win all of these, let's count. Remember what our probability is. Whoops, need a pen. The probability of winning, right, is the number of ways you can win over the number of ways in a sample. Okay, now, if each ticket has 2 chances to win and you're buying 1 ticket, there's 2 ways you can win this. Okay, typically in our lottery here, this would be a 1 up there. You match everything on the ticket and you've won. Apparently they have 2 sets of 6. So the number in the sample. Okay, so there's 52 balls and you need to choose 6 of them. Okay, so let's put this on our calculator. 2 divided by 52, choose 6. Okay, and once again I got scientific notation. I got 9.8238 ... e to the negative 8. Now let's write it down here just to go through that again. 8, 2, 3, 8, 9, 6, 8, 2, 6. And this time it says the exponent's negative 8. That means I've got to move my decimal 8 units in the negative direction. So 1, 2, 3, 4, 5, 6, 7, 8. I've got to add 7 zeros to that. 7. Okay, and then let's round it there. Basically 0. What's the probability that you're going to win the lottery? Pretty close to 0. Okay, but once again, we can use these counting techniques to help us do our probabilities, and that's our whole goal, right? Doing probabilities. So you just count the number of ways the particular event can happen, okay, and the number of ways the sample space can happen. Okay, let's do one more. A shipment of 120 fasteners that contained 4 defective fasteners was sent to a manufacturing plant. The plant's quality control manager randomly selects and inspects 5 fasteners. What is the probability that exactly 1 of the inspected fasteners is defective? Okay. Oh, shoot, sorry. Pen. Okay, probability that we get 1 defective. Well, that would be the number of ways that you can choose one that's defective. Now, let's look at this issue again. Make sure we consider everything. Okay, we got 120 fasteners, 4 defective. So let's put it down here. 120 total, which gives 4 defective, which means there's 116 good ones. Okay? We want to know what's the probability that we're only choosing 1 defective. So I might choose that one out of this 4, right? Because we're choosing 5, right? So out of this 4, I have to choose 1 if I'm saying that 1 is defective. Okay, let me try to reword that. Okay, so I want to know what's the probability I'm going to choose 1 defective, but I'm reaching in and I'm grabbing 5. So 1 of them has to come out of this 4. Now the other 4 has to come out of the good ones. So then there's 116, but I'm going to choose 4 of those. So notice what has to happen here is this is my 5, right? And this is the 120 that I'm choosing them out of. All right, now remember our fundamental counting principle. I don't add these together, I multiply them. Right? When you're counting the number of ways something can happen, you multiply them, don't add them. And then it's over. Just what's the total ways you can reach in and grab 5 out of that 120? Well, that's 120. Choose 5. Okay, so on the bottom, it's just any way you can get 5 out of the 120. But on the top has to represent your event. You're choosing one defective. So it has to come out of the 4 broken ones. But because you've grabbed 5, that means the other 4 came out of the other 16. Now notice also what happens when we do this. This has to match, and this has to match. Okay, so once we get our formula, then it's just a matter of plugging it in our calculator. So we have 4, which by the way, guys, anytime you choose 1, this number right here is going to be 4, right? Because how can you choose 1 out of those 4? Oh, you get the first one, the second one, the third one, or the fourth one. Okay, so if we do that like we just said, that's 4. Okay, and then I'll get 116. Choose 4. That's and then it's all divided by 120, choose 5. Hey, and if you don't know, here's another little shortcut for your calculator. If you just hit second enter, because getting over to those factorials and combinations and permutation operations is a kind of a pain. But once I have this entered in here, if I hit second enter, it brings that right back up, and all I have to do is go over and change the 116 to 120 and the 4 to 5. So I don't have to keep going back in once I've entered it one time. 78024. Okay, so I could do this, write down each individual number, and then plug it all in for my final answer. Or I could have done it here, all in one step in my calculator, right? Whatever you prefer. I was just kind of doing this for emphasis, right? Here's our number, here's our number, here's our number. And it might be shorter to do this because we can do that second enter. And once I've entered this, then second enter, I can do this and then go back. But I don't know. Now I've got to enter these long digits. So whatever you guys, however you prefer to do it. 60245 divided by 0578024. Okay, so let's round to, let's say, the 4th decimal place, 0.1503. Okay, is the probability that if you reach in and randomly grab 5 fasteners, you'll have 1 in your hand that's defective under these conditions. Okay, let me know if you need anything.